Good afternoon, everybody. Who just arrived? David is here, and oh, both of you. All right. That means we've got everyone here on time, ready to go. Then let's get to it. So, in addition to poo-pooing on Superman, as we are wont to do, I've got a few announcements since the end of the year is nigh. Prepare now. There is information that you need before we get to the actual heart of the math topic. First up, please note all the classes will be online next week, so you stay home. Okay? But you're still log into Zoom on your appropriate color day, check the schedule there, which one that is. Otherwise, it works all the same. Wednesday is slightly different in that it'll be much shorter. We have a half day, so all of the classes have been reduced to only 30 minutes long. Our class specifically, I have scheduled that to become more of a work day / catch-up day. So you'll just be using that to work on whatever assignment you have still to work on that day. All the usual stuff is there. Monday and Tuesday has the regular classwork for class. You've got the weekly homework on study.com. That'll be there. You've got on Wednesday, there will be the SAT practice will be posted. So you can just take that 30 minutes, plow through that SAT thing, have it done, finished, so that all that stuff that would still usually be due on the Friday, you don't have to worry about the whole weekend, right? It'll be great. I myself specifically will be even more remote, not only from home, but on Wednesday, I will be tuning in from my parents' house. Okay? So it's going to be real simple. You log into Zoom, I check that you're here, I check that you're working, and that's all I hold against you. There's nothing more to it than that, right? That said, much more complicated is the actual end of the year, the final exam. Okay? Same final exam structure as every year. You've got a specified time based on the class and the date. Okay, that is put on my master schedule, so you can just look straight at that. Everything for the math class you need right there. The week before that, we will spend reviewing. And so that'll be a review packet I'll post, and we'll just work on that throughout the week. And then at the end of that week, you will take the review quest. And I call it a quest because it is a quiz-is test. That is to say, it'll be a quiz-is, but it'll go in the test category of points. So it's worth a whole lot more, which means it's going to have a much bigger impact on your grade. But it's a quiz-is, so you can go back and retake it as many times as you need to. Some of you haven't been taking advantage of that feature, not full advantage of that feature, to get that 100% on your quiz scores. This is a chance to get a 100% on a test score. Please do not squander that opportunity. It's an awesome opportunity. Basically, you can you can do a lot for your grade there, okay? So keep your eye out for that. In addition to then, the regular final exam test will be electronic at the exam time. We'll talk more about that when we get closer to it. Okay. Any questions then on this announcement stuff? No? Then let us move on to our mathematical topic for today is the great and glorious Pythagorean Theorem. Yay! I really want that soundboard so I can have a little cheer section. It'd be great, because you guys are just too quiet. Anyways, the Pythagorean Theorem, possibly the most famous of all math theorems, the one that everybody seems to know. Certainly the most famous geometry theorem. Everybody seems to be familiar with this equation. You've probably heard it before, right? So fill this in for me. For any right triangle, emphasis on right, it only works on right triangles. If we call the sides A, B, and C, with C being the hypotenuse, Pythagorean theorem says, anyone? I'm listening. Someone's got to know it here. Do you know it? What's the Pythagorean theorem? What's the equation?
A squared plus B squared is equal to C squared.
Ooh, David's got it. Thank you. I think you were close there. A squared plus B squared equals C squared. And this is a simple formula to find the third side of a right triangle. Given any two, if I know A and B, I can plug those straight in, solve for C. If I know B and C, we can just subtract one from the other and solve for A, right? It's not too crazy to work with, but it shows up a lot because right triangles are everywhere. So real quick, let's practice one. Give me any two numbers for A and B, within reason.
5 and 10.
5 and 10, I like it. Okay, straightforward. Replace A and B with those numbers. Order doesn't matter. I'm going to write the 5 first, just because. Is equal to your C squared. Go ahead and square it. 5 squared is 25, plus 10 squared is 100. This is where it'd be a really good idea to review that diagonal on your multiplication table. So C squared, so results of 125 equals your C squared. And then the final result, because I just want C, not C squared, we've got to undo that squaring by square root both sides. So C is equal to the square root of 125. I don't think that has a perfect square result. We can check with the calculator, right? 125 square root. Yeah, 11.18. There's your decimal approximation. About 11.18. We could probably have guessed close to that. So here's your exact answer. It's more than 100, so it's more than 10. 11 squared is 121, right? So it's a little more than that, a little more than 11. So just to conceptualize it there. Right? That's all there is to it. That's using the Pythagorean theorem. Find the third side of a right triangle. We see it all the time, and that's going to be most of your practice. Any questions on that so far? That's the basics. And if this was a middle school level, we would just leave it right there. But this is high school. Let's dig in a little deeper, because there's a few intricacies related and some neat historical nuance to this thing. Because despite being named Pythagorean Theorem, Mr. Pythagoras, the Greek mathematician, was not the only one to come up with this idea. It's just the one we stuck his name on it. The ancient Chinese, they knew about this. We've got historical evidence of Chinese civilizations with this pattern, this a squared plus b squared equals c squared. They knew of this equation, this relationship. Egyptians knew of this as well. In fact, they used this to help build. How could they have used this and a piece of rope to form a right angle? I want you to think about that for a moment. How the heck can you make a perfect right angle with only a piece of rope? Rope, you mean the dangly stuff. It's not straight, it's not solid. How do you bend it into a right angle and make it hold? Well, they did a very tricksy thing. They were very clever, these ancient Egyptians. Here's what they did. First, you take your rope and you tie it into a loop, okay? Tie it into a knot there. And you're going to get 3 guys. One pulls this way. One pulls that way, and one pulls this way. And so you pull that loop taut into a triangle, more or less, right? And then here's my bow. You get a rough shape kind of a triangle, and the tighter you pull it, the straighter you can make those lines, because that's the one thing you can do with rope. You pull it taut, right? So they would pull on these corners to make it taut. And so you'd have a nice straight-sided triangle. But how did they make sure it was a right triangle? They set it up to be a Pythagorean theorem sized triangle, they would put additional knots in the rope to divide it up into sections. So we could have 1, 2, 3 sections here. We would have 1, 2, 3, 4 sections here. And then 1, 2, 3, 4, 5 sections there. So they could just count by everybody grab the correct knot and pull. And a 3 squared plus 4 squared equals 5 squared. I know I'm guaranteed that corner to be a right angle. Right? And then they could use that. They could pull this rope over and, hold it over top of their building project and, lay it on the ground and then line up their bricks to match and everything. And you'd have this perfect right angle without having, because they didn't have, a steel carpenter's square from the hardware store back then. Right? That's pretty nifty. In fact, what that does for us is it actually uses Pythagorean theorem backwards, right? Instead of knowing it's a right triangle, then calculate the measurements, they put known measurements to then understand that it had to be a right triangle. We would call that the converse. So it turns out the converse of the Pythagorean theorem is also true. If a squared plus b squared equals c squared, then the triangle must be a right triangle. So you can use that as a test to see if a triangle is a right triangle or not, if it conforms to this equation, which is really useful because a lot of the times we have a way easier way of measuring lengths. We can measure the 3 sides of the triangle pretty easy, but not everybody carries around a protractor to measure and check. Okay, is that angle actually 90? Is it more like, you're only 89 degrees here, you're a little off, right? Nobody carries around a protractor anymore, but we have rulers and tape measures all over the place. So you could check things to see if they're square using this method. Pretty handy, huh? Okay, any questions on that concept there? All right, seeing none, I have one last thing for you to add to Pythagorean theorem. And they're going to be super handy. You're going to love this shortcut. That is the Pythagorean triples. All right, our example earlier, when we tried it out, what was 5 and 10, and we got 11.8, 11.18? 11.18. That didn't turn out very nice. We got this awful decimal that just went on like forever. Look at this thing. Gee. Wouldn't it be great if we could have gotten a nice, beautiful integer answer? Turns out, a lot of people thought so, and so they started keeping track of the numbers that work out nicely and always give you an integer answer in the end. And we call those sets Pythagorean triples. 3 squared plus 4 squared equals 5 squared exactly. And the Egyptians made use of one of these, right? In their knotted rope. And we see these all the time because humans, by nature, seem to love integers way more than decimals and fractions and all that jazz. So we see these come up as the most common triangles, at least as far as like problems and invented scenarios are concerned, not real-life measurements. So I would recommend to you to go ahead and at very least write this down and have that at the top of your sheet when you're working today. But start committing these guys to memory, because the faster you can recognize these, the more work and time you get to save yourself later, especially on the SAT. The SAT loves its triangles, and the most common type of triangle on the SAT is the right triangle. And the most common right triangle on the SAT is a Pythagorean triple. And the most common Pythagorean triple is the 3, 4, 5. I would say then the next would be the 5, 12, 13, then the 7, 24, 25. and then the 8, 15, 17, like kind of in descending order there is most common to less common. In fact, we've seen one of these before. If you were paying close attention, you might recognize this set of numbers. Anyone know where it's from? That's right, it was from our volume questions. Yeah, that's how we did this, right? The diameter was given at 14, so half that is the radius, which you needed anyways, is 7, which is the leg of this right triangle. We didn't know the height, but we did know the slant height, which is the hypotenuse, that is to say the longest side across from the 90-degree angle. 725. Ooh, that's 2 out of 3 numbers of my Pythagorean triple. So I could know instantly, without having to run the calculation, 724, 25. I can just fill in the missing number there. That saves you all kinds of time. You don't have to write anything down. You don't have to compute it. Square 24. Oh gosh, right? Who knows the square of 24? I don't. I know the square of 25, actually. That one's pretty easy, 625. But I wouldn't have done this without a calculator, right? Unless you memorize this triple, and then it's no work at all. And the SAT loves to throw these things at you. So you can save all kinds of time and effort by committing those guys to memory. Even better, this list is infinitely expandable because it's these guys and their multiples. You can take any set and multiply the 3 numbers all by the same thing. Say you want to double it. Double it up, 3, 4, 5 becomes 6, 8, 10. Or you could triple it. Multiply everything by 3, 9, 12, 15. Also Pythagorean triple. Also still a right triangle, because all you've done is you've scaled up the triangle, but you've kept everything in proportion. So it still works out. Still a right angle. That's really handy, especially because, again, the SAT loves these things, but they also love to be tricky. So very rarely will you actually find the 3, 4, 5. You're more likely to find a 6, 8, 10. They try to hide it from you. So if you know that trick on it, you're like, oh, this is a 3, 4, 5 triangle. You'll see hidden 3, 4, 5 triangles everywhere. Okay? Any questions on those guys? All right, then I leave the rest of the work to you. You have these 10 exercises to complete for today, all based on the Pythagorean Theorem, finding the extra side of a triangle. Keep in mind the additional information involved in these problems, such as coordinates, and you really need to know much about a circle other than the radius would be AB here. Which, oh, look, that's the hypotenuse of this right triangle. Finding side AC is pretty simple. Once you work out what C has to be to line up with A and B, you just subtract the 2 values there to get the length. And then you get same thing here, Pythagorean theorem, you got it, right? So it's a bit of a trickier setup in context, but the computation is no more difficult than usual. Same with number 8. Number 8 looks complicated, but do watch out, you're not really paying any attention to this triangle, TRU. That triangle is useless. Pay no attention to it. Instead, treat this as a stack of right triangles, each getting longer and longer. You're still involving side RS every time. Okay, use that to find one length, and then use that to find the length of the next one, and that to find the length of the next one. So keep working on those right triangles there. And 10 might be a little tricky there when you eventually want to get find the altitude. Okay, altitude is going to be perpendicular. Just remember, it's got to be a right triangle. All your calculations are based on right triangles. Just remind yourself of that. How do I get right triangles here? Okay? But it's still not too bad. Again, just draw the picture and label it properly. It'll work itself out. All right, so any questions at that point? No? Okay, then you have your work laid out. I will leave you to it. Please let me know if you do come up with any questions. I'll be happy to help you out.